All right, we're going to look at this construction. Let me do it on there. If you haven't finished yours already, we're going to I'm going to make a dot where I want my right angle. That's the most important part, is because we're talking about proportions in right triangles. So it's got to have a right angle here. So first thing I'm going to do is just draw a line from my dot just down. I don't have to worry about the length right now at the moment. Okay, and then I'm going to I'm going to bring out my protractor and find a 90-degree angle. Okay, so we'll put that right on here. And so you see how I've got my protractor right on the end of my line there, and it's going right through 0 degrees. Now I want to make it go through 90 degrees, so I'm going to make a dot right where 90 degrees would be. And then I can move my protractor. I can then set up my line here and make it go through that dot. So that makes sure I've got a 90-degree angle. That's the main thing. I want 90 degrees. I also need them to be an 8 and a 6. So that's going to need a ruler, or you might have the ruler on your protractor, but I'm going to need an actual ruler here to measure it. So I need my first one to be 8. And I was almost right on the money, just a teeny bit short there. So let me lengthen that just a little bit. Okay, so you can see 0 up to 8, that's 8 centimeters is that one. And then my second line I need 6. So let me put this here. And see where 6 would be. 6 is right about there. It's pretty close. Okay, so got my 8 and my 6. Before I connect them, I want to verify that I'm still at 90 degrees. So, and that looks pretty good. It's going right through 90. It's going right through 0. So I know I've got a 90-degree angle. I can simply connect my 2 endpoints and make a right triangle out of it. So that was the first part. Now notice it doesn't have to be going the exact same direction. You just need to have a right triangle. So you should actually, in your little box, little angle up here, put a right angle box so that you know you've got a right triangle. Now we're taking out our compass. So here's where we want to do the little construction. We call it the smiley face. And you put the compass on your right angle. And you just have to make sure that it's opening up past the hypotenuse. It's just got to open up a little bit past the hypotenuse. So I'm going to go to about there. That way, when I do make the arc, it should intersect the hypotenuse in 2 places. You see the 2 places where it touches my hypotenuse? One of them is right where my compass is right now. So if you look at my compass is right on that point where it touches the smiley face touch the hypotenuse. That's going to be one of my arcs for my X. And then I move it to the other place where the arc intersected the hypotenuse. And then I draw in the other arc and I get an X down there at the bottom. So the last step will be to connect your right angle, the dot where your right angle is, and your X. Connect those 2 together. And then you want to verify to see if you got it right. You take your protractor and you measure the angle that that line made. If you did it correctly, it should make an exact right angle. Interesting. Yeah, it's about 90. My compass won't go exactly where I want it to go, but there you go. So it looks right at about 90 degrees. So we brought down a line perpendicular to our hypotenuse is what we did. It's perpendicular to our hypotenuse. You could actually put a little box in here as well and show that you made a right angle. So that is the construction that we wanted to do today. That's what we're going to be talking about, is what happens when we bring down a line from the right angle and make it perpendicular to the hypotenuse. We're going to find out what that actually does to the triangle itself. So you can see that we're dealing with a right triangle. And our next unit is our trig, one of our trig units. So it is all about right triangles. So it'll be good to see how the right triangle proportions work as we build into our trig unit coming up next. And trig is one of the best, I think, because trig is real life stuff. I mean, we could go outside and measure stuff and figure exactly how tall stuff is just because of trig. So, you know, it's a good real life unit. So I like the trig unit coming up. But if you notice, if you notice this first one that I did for you, the CD right here, if I move D to where this right angle would be, if you notice this CD, what would we call this line in this triangle? It has a special name. A lot of people were saying perpendicular bisector earlier. But does it bisect the hypotenuse? No, it doesn't. What do you think? Okay, well, does it bisect the angle? I don't think it cuts the angle in half. Transversal would be cutting through two other lines. Starts with an A. And it's something that we just did in Euler's line. Starts with an A. Like if you're flying in an airplane and you want to know how high up the airplane is. It's the altitude. It's the altitude. In other words, it's the height of our triangle. It's how high the triangle is from the top part to the bottom part of that side and that angle. That's called the height. It's the altitude of the triangle right there. So when we brought it from letter C straight down to the hypotenuse. That is a right angle. It's a perpendicular line to the hypotenuse. We call it the height or the altitude. Now, I don't know if you remember, but in Euler's line, we found all three altitudes, one from each angle. And they met at a place called the, starts with an O, orthocenter, right? It's the orthocenter. In a right triangle, just as a side note again, we're not studying this today, but in a right triangle, the orthocenter is the right angle. So if you notice that AC would be an altitude because it's a right angle, BC would be an altitude because it's a right angle, and DC would be an altitude because it's a right angle. What letter was in all three of those? C. There's my orthocenter. They all meet at point C. So in a right triangle, C is your orthocenter. They all meet right there, the altitudes. But what construction did we just do in this picture when we did this little smiley face? What were we actually doing? We call it the smiley face, but what are we actually doing in the construction? What is our goal of that construction to draw? We're drawing perpendicular, right? So we're drawing perpendicular line, perpendicular line to another line from a point not on the line. So what we're trying to do is make a line that's perpendicular to another line from a point that's not actually on the line. Point C was not on the hypotenuse. Point C was the right angle. We're trying to make a line perpendicular to the hypotenuse from point C that wasn't on the line to begin with. That's what the smiley face does. Now, if point C was on the line, you could make a different smiley face and it would still work. But this is the smiley face that we use when the point's not on the line. It makes a perpendicular. So let's study actually what that does. Let's take our protractors out again. Okay, grab your protractor and measure this angle right in here. And let's hope and pray we get about 38. And 37 to 38 should be where we're at. And that's pretty much what I got, I think. Yeah, and I'm about 37 and a half. What are you guys getting? 37? All right, we'll call it 37. So you might have 37 and a half. You might have 38. You might have 37. But let's call it 37. So we're just going to round it to a whole number so we can look at it just as a whole number. It might have a different angle exactly, and Trig actually could give it to us, which we're going to do in the next unit. So that's why it's cool. Trig, it really gives us a lot of stuff. But we're going to call it 37. Let's measure the other one, or do we need to measure the other one? We don't really need to, do we? Because I've got a right angle, and I've got a 37. And what do I know about all three angles here? Add it to 180, and if one of them is already 90, what do the other two have to add up to? 90, because 90 plus 90 is 180. So what's going to make 37 add up to 90? 53 degrees. So you can double check it if you want to. You can make sure that it came out 53. If you got a 37, you should end up with a 53. So that takes care of the big triangle. What do you think happens when we drop down that altitude? What do you think it does to these two angles? Well, let's find out. I want to measure one of these angles. So let's measure this smaller one. So put your protractor kind of like that so you can measure the angle. Okay, you see how I put my 0 is on the altitude and I measured the actual angle up there at the top? Measure that angle and see what you get for your angle. What does mine say? Do you have any idea what mine says? Here's 10, 20, 37. So it looks like this little angle right here, for me, was 37 degrees. That looks kind of familiar. Didn't I just have a 37 a little bit ago? Yeah, so that's kind of interesting. So what then do you think my other angle right next to it's going to be? Why do you think 53? Because it makes the right angle, doesn't it? Aren't those complementary? They have to add up to 90? So yeah, it's got to be 53. So kind of looking at this picture now, we've got two 53s and two 37s. So this altitude right here made the same two angles as the right triangle had at the beginning. Now let me ask you this. Do you see three triangles in that picture? Do you see a small little one? Okay, that's this little guy right here. What are my angles in this small one? 37, 53, and 90. Do you see a medium size? That's this one over here. What angles do I have? 53, 37, and 90. Do I see a large? 37, 53, and 90. So you can pretend like you're at a fast food restaurant. You order a small, medium, or large triangle. Just triangles. All right. But what do we know about all three of those triangles? Proportional to each other means they have a special name. Similar triangles. Anytime that we have proportional sides and congruent angles, they have to be proportional, right? They have to be similar triangles. So this altitude right here made three similar triangles. That's what this right triangle theorem says right here. Here's what it says. The altitude, if an altitude is drawn to the hypotenuse, if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to each other and to the original triangle. If an altitude is drawn from the right angle to the hypotenuse, then it makes three similar triangles. That's what it's basically saying. You're going to be making three similar triangles. I tried to do you a favor and show you what the three similar triangles look like when I spread them out. So I broke them out on the picture right below what you have on your notes. But I'll give you a second to finish that. An altitude is drawn to the hypotenuse of a right triangle. The two triangles formed are similar to each other and to the original. This is a picture of the same thing that we just drew. It has CD as an altitude, right? The altitude goes to the hypotenuse. Okay, we're good with that? And you've got a small leg, a medium leg, a longer leg, and then the hypotenuse of the big one. And then you've got all your little triangle and your medium triangle. What I did for you is I broke them out so you could actually see them all going the same direction. So my little triangle is right here. It's got a short leg of 1.6 on the bottom, and it's got a longer leg of x. Okay, do you see that in the small triangle? Short leg, long leg. Now the medium triangle has a short leg that's x, and the longer leg is 3.6. Okay, we okay with that one? The entire big triangle has no legs as far as the numbers on the legs, right? But we could add the hypotenuse together. What would we get? What could our hypotenuse actually be? 5.2. If I wanted to put that here for this hypotenuse, I could put 5.2 meters. The problem is that 5.2 meters is not really going to help me because I don't have a hypotenuse of the small one or the medium one. So having this hypotenuse, I don't have any other hypotenuse. So I can't really use that 5.2. But look at these legs down here. This x matches up with this 3.6, doesn't it? They're both the back sides. This 1.6 matches up with this x. They're both the bottoms. So the sides, we do have corresponding sides there. Where we're at is that we're looking at these two legs right here. And could we set up a proportion that would allow us to solve for x using those two legs? I'm going to start you with 3.6 over x. So if I put 3.6 over x, what I'm putting is I'm putting the medium triangle's back leg, or long leg, over the small triangle's long leg. So I'm doing long leg over long leg, and I'm doing the big one, the medium one to the small one. So what other fraction could I use that would allow me to solve for x? I did 3.6 over x, so I would need what? X over 1.6. That would be the short leg over the short leg. So I did long leg over long leg equals short leg over short leg. So let me make my lines there, and let's solve this. So if I was to solve this, I get x times x, which is x squared. I get 3.6 times 1.6. I actually solved it over here. So I solved it down there so you could actually see it. So I did x times x, I got x squared. I did 3.6 times 1.6 and got 5.76. And then I square rooted both sides because I don't want x squared, I want x. I want to know what x equals. So x equals 2.4. This line right here, notice this x. Do you see where it was in both of my proportions, or both my ratios? That x number was in both of them. And it was in a special place. The place that we call it is we call it the means. Now you might have heard that before, a couple sections ago. I was showing you proportions. And I said we have the extremes and we have the means. So you have like A, B, C, D. A over B equals C over D. A, B, C, D, A and D are your two outside numbers. They're the extremes. So this is an extreme and that's an extreme. B and C are your two inside numbers. Those are your means. So you've got your two means, B and C would be your two means, the x and the x. So you got your two extremes, you got your two means. In this problem, and in any problem where you have a right triangle and you've got an altitude, that altitude is going to be what we call the geometric mean of the two pieces that it breaks. It's always going to be the one that's in the two mean places. So if you look at geometric mean here, here's what a geometric mean is. Now let me move this and I'll put this up here. If I could grab it. There it is. The altitude to a hypotenuse in a right triangle is the geometric mean to the two segments of the hypotenuse. So the altitude, this goes down where the stars are. See the stars right there? Put this next to the two stars. The altitude to a hypotenuse in a right triangle is the geometric mean of the two segments of the hypotenuse. Okay, so let me show you where that is. The x is the altitude that you're making to the hypotenuse. That x is what we call the geometric mean of the two pieces that it breaks, because it's going to be in the two mean spots on our proportion. The two numbers that it breaks is going to be in the two extreme spots. So we call it the geometric mean. How you solve for a geometric mean is pretty simple. A geometric mean is the square root of the product of two numbers. And that's exactly what we did to solve it. We multiplied 3.6 times 1.6, and then we took the square root and we got our answer. So it's the square root of the product of the two numbers. That's what you want to put under geometric mean. Next to the two stars, you were supposed to put the altitude to a hypotenuse in a right triangle is the geometric mean. That altitude line that we drew is the mean of those two pieces. You put that in the two mean spots, you multiply the others, you take the square root, you have your geometric mean. Move it up a little for you guys. So it's the square root of the product. I don't know. There it is. Sorry. It's the square root of the product of two numbers is the geometric mean. So we're just going to practice a couple of them, and that's it. And there's a few of them on the school net tonight that would also be for you to practice. But if you know that this x is going to be in the two mean spots, and then your numbers are going to be the extremes, multiply them, divide, get your square root, you'll get it pretty easily. Okay, so this little example that was next, it says find the geometric mean of 4 and 5. Well, we know that we're going to multiply 4.5 and square root it because it's the square root of the product. But I want to see where it would actually set up on our proportion. So let's see if we can actually make a proportion for the geometric mean of 4 and 5. What would I need to put on top? 4 over x, right? Because x has to be in a mean spot. And then what would be my next proportion? It'd have to be x over 5. Your x has to be in the other mean spot. So you'd have 4 over x equals x over 5. And then you could multiply your diagonals. You're going to get x squared equals 20. And then you would just square root both sides. So you could see that you took the product of 4 and 5 and then square root it. It's the square root of the product. So we're going to square root x squared. We're going to square root 20. Now you could get your calculator out and find out the exact value of the square root of 20. And you would get 4.47. But does anybody remember how to break down a radical into a smaller radical? You got to find a perfect square that can come out, like 4, right? So 4 and 5, a square root of 4 is 2, so you could put actually 2 radical 5, and that would be the same answer. So I think more importantly, you need to make sure you know how to get it on the calculator, because most of the time they'll probably be asking you to round it to the nearest 10th or 100th. But you may need to also break it down, so know how to do that. 2 radical 5 is the same. Okay, there's just a couple of little ones left, little pictures, and they go pretty fast. So let's take a look at the first one right here. Solve for x. So this has 9 as my altitude. Now remember the little thing that I told you to write. The altitude is the geometric mean. So that means this 9 is the geometric mean. So guess where the 9 is going to go? In the 2 mean places. This time it's not going to be x, it's going to be a 9. So what would be the proportion that we'd need to set up? X over 9 equals 9 over 4. Or you could do it the other way and do 4 over 9 equals 9 over x. Either way, you just need to make sure your 9 is in the mean places. Your 2 means have to be 9. 4 and x are your 2 extremes. The 4 and the x are the 2 outside numbers. So when you solve this, you get 20.25. What that means is that if I multiplied 4 times 20.25 and then square rooted it, I would get 9. And it does work, because 4 times 20.25 is 81. And the square root of 81 is 9. So 9 is the geometric mean of those 2 numbers. So that does work. This altitude is always our geometric mean of those 2 because of similar triangles. We know it works because we drew out the 3 triangles and we set up the proportions and it worked. So how would I set up my proportion in this next one? Remember, x is my mean. X has to go in the 2 mean places. 8 over x could work. Then you could have to do x over 2. What if I did 2 over x? X over 8. Yeah, so you could choose either one. I did 2 over x equals x over 8. And so I did x squared equals 16. Now remember, you're multiplying the 2 numbers and then square rooting them to get your answer. It's the square root of the product. So you got x equals 4 for that one. What about my last one there? Okay, 10 over x equals x over 10. Yeah, you got to have your x in your 2 mean places. 10 times 10 is 100, so you're going to square root 100. You know you're going to get 10. So square root of 100 is 10. All right, I'm going to get rid of these 3 on top, so hopefully you've got those done. I'll leave it for a second. And I need to get rid of those 3 so I can move the other 3 up. So we good on those or not? Okay, I'm going to get rid of them. We're good? Oh, oops. Oops. What did I just do? Get rid of that. Interesting. All right, let's see what happens here. There was a box there, huh? Lost it. It's back again. I got you mad gab today, Jonathan. All right, so let's see. I'm not promising I can come up with the answers. I might be able to. Okay, let's look at this first one. Now this one, we can't really use the geometric mean because this amount is x, but we don't have the 2 pieces. We know they're going to add up to 16. We just don't know exactly what they're going to be. So we need to do the similar triangles instead. So if you notice, this x right here is the long leg of my little triangle. You see that? And the 9 is the hypotenuse of my little triangle. So if I did x over 9, which would be long leg over hypotenuse, What one would I need to use for my big triangle? 12 over the hypotenuse of 16 is the hypotenuse, right? The big 16. So let's use that one. It's going to be x over 9 equals the 12 over 16. Now I would reduce if I was you guys, because you don't want 12/16ths. It's kind of too big of numbers there. So let's do 3/4. Let's reduce that to 3 over 4. Now you can multiply your diagonals. You'll end up with 4x equals 27. And when you solve it, x would come out to be 6.75 if you do it on a calculator. If you do 27 divided by 4 on your calculator, you get 6.75. So I had to use similar triangles to get it this time. I had to use the long leg over hypotenuse equals long leg over hypotenuse. Now I could put LL over HYP just to remind myself that I did long leg over hypotenuse in both of them. Both of them were a long leg over a hypotenuse. As long as I'm consistent, I can set them equal. So if I do long leg hypotenuse in one, I got to do long leg hypotenuse in the other. And then I can solve for it. The next one, we don't have the altitude this time, so we can't use the geometric mean. But we could use the similar triangles. What is the 4 representing of my small triangle? It's the short leg, isn't it? And isn't the 8 the hypotenuse of my little triangle? What about the big triangle? What's the 8 in the big triangle? Short leg. What's my hypotenuse in the big triangle? Thank you. X plus 4, not 4x. We're not multiplying them. X plus 4. They're going to put those two together. So I've got a short leg over a hypotenuse. Short leg 4 over hypotenuse 8. Whoops, it's gone. Okay, so I'm going to use 4 over 8. And that's going to equal my short leg, which is 8. Ooh, that's a geometric mean, isn't it? Geometric mean, this piece is the geometric mean of this short leg and the hypotenuse. So, if we wanted to use that. But we're going to put x plus 4. We just figured that out by using our similar triangles. Alright, so let's draw our lines in there. Alright, let's, I would reduce again. 4/8 you could reduce to 1/2, right? So make that 1 over 2. Multiply your diagonals. And you get 16 equals x plus 4. And then when you solve for x, you get 12, right? 12 equals x. So think about this. If I put a 12 in for my x, how long is the hypotenuse of this triangle right here? 16, not 48. That's why I don't want you to ever think it's 4x. You don't multiply those two numbers together. If you knew the two numbers, you would add them. So you got to do 4 plus x, or x plus 4. Okay, what about this last one? Okay, so. Okay. All right, so we've got every piece of the little triangle. We've got an x for the short leg, a 3 for the long leg, and a hypotenuse of 4. What do we have in the big triangle? Part of the hypotenuse. Yeah, we don't have the whole thing, though. We got the short leg, don't we? And we have the long leg. So let's do short leg, long leg. Let's do short leg x over long leg 3. So x over 3, that's for my small triangle, x over 3. And in my big triangle, what's my short leg over long leg? 4 over 10. So that would be the short leg, long leg. And again, I would probably notate yourself somewhere so you don't forget how we got these, is I might put short leg over long leg. And then I might on this side put short leg over long leg, just to remind myself that that's how I got the proportion. I did the 2 short legs on top, the 2 long legs on the bottom, to make sure that they're equal. And you could reduce the 4/10, right, if you wanted to. You could make it 2/5. So 2/5. And then let's see, 5 times x gives us 5x equals 6. And then if you divide both sides by 5, you get 1.2 for x. So, and it has to be less than 3 because it's a short leg and 3 is a long leg. So 1.2 is less than 3. So that's what we get when we make an altitude and a right triangle. You get similar triangles. Same angles, proportional sides.